So my claim is now that every choice of cellular automaton, every choice for its evolution law will give me a quantum theory. One can compute what will happen when particles collide, at least if you know exactly what to look at. But that is extremely difficult question what to look at. But any theory described by any cellular automaton, a local cellular automaton, so the interactions should be interactions between neighbors only, then it will become a quantum field theory. And in principle, you should be able to compute all the kinds of particles that are there and how they interact. It works in two directions. I can also start with a theory such as a standard model, and in principle, derive what cellular automaton will generate this behavior. I add the words in principle. In practice, it is very difficult to do so, but at least I know what the questions are, and all we have to do now is try to answer the questions. So with respect to this theory, we are very close to quantum field theory before the 1970s, when we started to learn how to fill in the rules. I don't know what the rules are. So let me begin with a prototype of a quantum model that explains to you how to think and how to work in such a theory. This, what you see here on the left of this picture, is a chain of states. I label them 1, 2, 3, all the way to some integer n. If you look carefully and are able to count, you find that in this example, n is 11, but n could be any number. It could be very large, could be very small. But this is the prototype of models I'm looking at. In such a model, the object can be in n different states. The different states, all this n, which is in this model, looks like 11 different states, tell you exactly the classical states this model can be in. So I'm discussing here a classical model. And the law of evolution for this classical model is extremely simple. It just says there's a clock on the background somewhere, the clock is ticking. And at every tick of the clock, whenever your particle were in position number 0, it goes to position number 1. If the particle is in position number 1, then at the next beat of the clock, it will go to position number 2. And so on until it arrives at the position n-1. When the clock ticks again, it doesn't go to n, it goes to 0. So it's circular. This model is a circular model, and the evolution law is indicated by an integer k running from 0 to 10 in this example. And the evolution law can be written down in a notation that looks like quantum mechanics. But it isn't quantum mechanics because I'm not using any Schrödinger equation at this point. I just use the law of evolution, classical evolution. And the classical evolution, I can represent that by a matrix, an 11 by 11 matrix, saying this matrix contains zeros and ones. On every row and every column, there are n-1 zeros, and there's 1 entry that's 1. This matrix acts on a vector k, which has zeros everywhere, except where the particle is sitting, there it has a 1. So you can imagine how this works mathematically. Acting with this matrix on the state where k has a certain integer value from 0 to 10, then it gives you the next value, which in this example is just 0, well, it's 1 to 11, but the 11th one is replaced by 0 again, so that this goes round and round and round. You also say mathematically that u acting on k is k plus 1 modulo n, and this matrix here is written as if it were quantum mechanics by 0 in terms of zeros and ones. But even though it's classical, you can still look at it as a matrix, and you can try to find a matrix called H such that U is e to the minus IH times delta t, where delta t is the time it takes for the clock to give its next beat. This is actually mathematically an easy exercise. I'll show you very briefly how it's done. But if you have such an H, you can also write down a state psi and say d dt of psi is minus IH of psi, where H is just the matrix, the matrix that solves this equation. And if you have this equation, you can check that this is indeed obeyed by the state. at every integer value, at every value of time that is an integer multiple of the beats of the clock, you will find exactly the state that your system will be in. So this is a way to write down classical evolution in a quantum notation. It is only notation, it's nothing more than that. So at this point, this is how you turn a classical theory into a quantum theory, by just doing this mathematics. In practice, the mathematics, for anybody with some practice of mathematics, finds this very easy. This is what we call the discrete Fourier transform, or the fast Fourier transform, where you're not integrating, but you're just making a sum over 11 entries. Here are all the 11 states. I indicate them by k being 0 to 10. This is an exponential, e to the 2 pi I times k times n divided by capital N. And you have to sum this over all values of k. Then you get a new quantum-like state I call n. But this quantum state now is no longer describing any particle in any position. It describes these things as a superposition. The reason for doing this is, well, eventually you want to understand how quantum mechanics works. But right now, it's also a convenient way to solve this equation. But to write down the general solution in a closed terms. The general solution is that these are the eigenstates of the operator U. Those eigenstates I can write down as e to the minus I 2 pi times n, little n, divided by big N. And then it is very easy to find the corresponding matrix H. So to find the matrix H, you have to do this calculation. And you'll find n states, which are the eigenstates of this U. And you'll find n different eigenvalues for U. All you have to do now is write them as e to the minus I, e every time. And then you get the matrix H that tells you how these states evolve. So this, what I write down here, is just a mathematical trick. It is not particularly difficult to solve them. What you find are n values for this number little n, for capital N values. Little n is indicating which bar you're looking at. These you can regard as energy levels. This state has n energy levels. They are equally spaced, as it turns out to be. So this is the solution of the Schrödinger equation for this model. You'll find 11 different states all at the same distance from each other. And by the time you reach number 11, you're at the highest possible state. You can write down more eigenstates, but actually they are mathematically identical to the previous ones. So you have to stop in this model after 11 steps. And you'll find this quantum mechanical system. There's one interesting mathematical question you can ask. You can ask what happens if I take this number n very, very large. Then you get what I call the continuum limit. This is the same picture as I had before, but now I take the continuum limit. The particle can be at any state on this circle. So now it becomes a more mathematically advanced way of writing at things. The particle can be anywhere. The sum I had before changes into a loop integral, the integral going around this loop. And here you get the sum again, but now the sum goes all the way to infinity. You go through the same mathematics, you find the same answer. You find equidistant elementary quantum states for the system, but now you get an infinite sequence of states, starting at 0, and they're all equally spaced, all the way going to infinity. Now you might, if you have some experience in quantum mechanics, you might immediately make an important remark, say, this looks exactly like the energy levels of the harmonic quantum oscillator. So the quantum harmonic oscillator has exactly the same states. So what I can also say is that this thing going around in circles now is a classical model that is mathematically identical to the harmonic oscillator in the quantum harmonic oscillator, because the quantum harmonic oscillator has these energy levels also. And actually you can say every state the quantum oscillator can be in, I can map them to a state for this classical theory. Except that most states you usually look at in the harmonic oscillator are superpositions of states of this thing. But the superpositions don't mean so much. If you want, you can say that the superposition coefficients represent probabilities. If you want, if you don't want, you can just say these are superpositions, period, and my model allows me to make these superpositions, there's no further physical consequence of that. It doesn't change the model at all. But you can say, I can now also treat the model using probabilities by taking that the squares of the coefficients of if you superimpose your states will represent probabilities. That is your choice. It doesn't matter. Mathematically, this is all equivalent to doing the same thing.
Question? I think
Yes,
I didn't understand this example. So where is stochastic some white noise, or I mean, why is this model different from quantum mechanical model?
It is not different from the quantum mechanical model. Sorry to interrupt. But I have not yet reached the point of dealing with stochastic effects. There's nothing stochastic in this model. It is completely deterministic, as you can see. So I started I started a completely deterministic model, and I'll introduce later what I mean by stochastic. Because in the very end, you're totally right. In the very end, you want a theory that reproduces the stochastic properties of quantum mechanics. Absolutely right. But I haven't reached that point yet. What you see here is many harmonic oscillators. And so, but with different periods. Some take a long time to go around, some go very fast. So, but I still have a clock that beats with one beat at a time. But now I can start in any one of these yellow boxes. I can start here, I can start here, and any of these, there are more than n now, boxes. And the rule is again clear. The rule is you make one step in this chain, but you see, you can return to the same value you were at before without having reached any of these. So if you are here in this circle here, you'll stay in this loop forever. If you're in this small loop, you stay in a small loop forever. If you're in any of these loops, you stay in the same loop. So this is the next step. The next step is, you can say, a more realistic model of the universe will be that you have a choice. You can be in different states of this oscillator, which each have different periodicities. So this is simply the next step, a little bit closer to what you are talking about, because you were thinking of having an infinite sequence of harmonic oscillators in an infinite chain. Well, that will be a next step again, to add infinity here. Say, I don't have 6 different models, I have infinitely many different models that my system can be in. Then what? It still is not stochastic. I have not introduced probabilities at all. I'm saying, however, you can, if you want, introduce probabilities if you want to. Then you can say, I have a chance that I'm here, there's another chance I'm here, another chance I'm here. And if I know these chances today, I know what these chances are tomorrow and the day after all the time. The chances will always be the same distribution, because the rest of the model is completely deterministic. So this is how I will talk about models, but I'm trying to go very slow. And so I haven't yet reached the stage of making infinitely many oscillators, but I will come to that. So it's a very important question. So right now you see that every single model of this kind has a certain sequence of eigenstates. So this thing here has only 6 eigenstates. This thing here has 8. The one inside is only 3. And here this is has 12, and that has 2, and so on. So all these different oscillators are there. Now, if you have in such a world, what are the energy levels in this world? Well, I have 6 different oscillators. Therefore, I have I think it's 5. Yeah, sorry, I'm 5 different oscillators here. So every oscillator here has its own sequence of states. There is this little thing with only 2 states has them very widely separated. The big oscillator, which has 12 states here, has them more closely separated here. So there's this sequence, there's that sequence, there's that sequence, and so on. So now I see that if you have a model where whenever you go around and you reach the same state where you were before, without having hit all the others yet, but you can also start in any of these other things, you have this situation that the energy levels form a more complicated pattern. What I can do next is put all these patterns together. So what I'm doing next is say, well, I squeeze all these, and if you look carefully, when you squeeze all these together into one sequence of energy levels, you find it looks a lot more complicated now.